Branch.
Okay.
The drill.
It's really. Where should I fork from?
That's special
The main
Okay.
branch.
Okay.
Okay, so whenever you're here, you open up Limelight Hardware Client. Limelight Hardware Manager. And then you find the Limelights. We're gonna use.
Just a little bit of that.
Okay. This one is the one that's physically to the left, and this is the one that's physically to the right. You just need to click. I think you need to double click on it. Yeah. And then now we can see the April tag and stuff. You're gonna need to make sure that your pipeline type is configured to April tags. This doesn't need to be this. Ladies on. This is fine. These settings are not the same as the ones that Limelight recommends, but it looks pretty solid, and you can see the tags. So that's all that matters. For configuration, this is probably going to be the one that it selects. Just make sure that that's the one that it's looking at. For this part, we're going to use full 3D targeting because we need to know the pose, the absolute global pose. But before we do that, we need to understand. Do you guys know what these are?
I can say that. I'll do it.
Yeah. So these are angles in degrees. So if I enable the robot, it's enabled.
You. One of the encoders.
Yeah, I think so. But it's fine. Basically, this so TX is how this from this point to the middle of the cursor, that horizontal angle like this, that's our TX. So if I align so that it's here, you can see that it's like that it's closer, so the TX is less. But as I rotate, it gets bigger and bigger. Positive TX value is always going to be whenever it's the cursor's to the left of the center of the tag, which is backwards from what you'd normally think, right? Usually right is positive, but Limelight is the opposite. The next thing is TY. TY is the same thing as TX, but this vertical, so up and down angle. A positive TY is whenever it's below the April tag. So like here, it's positive because it's below, and then it's negative whenever it's above.
So what the graph sees, what the April tag sees is a graph that's reverted.
Yeah, basically. And then TA is the percentage of the area that this tag is taking up, like how much of the screen. So since this is taking up more of the screen, it's bigger. And then since it's smaller, it's taking up less area. And then TL is the latency, so how many milliseconds it takes from it looking at the April tag to it sending it to the robot video. So that's about 6 milliseconds. The next thing is this is how.
Wait, do you change these codes to do auto align?
No, we don't change these. We're gonna change stuff in the actual code itself.
Yeah, in the codes you have these positions to change.
No, we have some. We have what I'm explaining here. So this. Okay, so this is this is kind of off, but this is the robot pose relative to the target. So this is where it thinks it is relative to the target. That's because right now that's where the April tag, that's where the Limelight thinks it is. So in order to fix that, we need to use this mega tag. We need to set this field localization up. So this is the position relative from the very bottom middle of the robot. How many meters up it is, how many meters forward it is, and how many meters to the side it is.
So it's the position of the line.
Yeah. So so you can, and also that includes also the pitch. So the pitch is the angles as well. what else is there? So then, yeah, normally I'd configure these. So you just you'd ask the counters the position relative to the dead middle. So touching the floor, middle of the robot. But the way that they've set up the localization or the, what do they call it? The auto line already, you don't need to do that. It's configured so that it's all zeros, which is not how we're gonna do it in the season. But I'd rather just leave it alone than have to retune it. And then also, oh, it's right here. So right now, this is the robot pose in the target space, which doesn't, like, you can't really tell what's going on, right? Like, you don't know where this is on the field. So you can change the view to robot pose in field space.
And this updates every single year.
Yeah. And so now you can see where the robot thinks it is. So the robot right now thinks it's floating. That's not great. But yeah, this is where the robot, if I change this to 10, then it'll make more sense. But yeah. Well, it's cuz okay, whatever. But yeah, this is where it thinks it is, and it's pretty, honestly, it's pretty close to where it is. If we change that ID out for something else like 7, I could,
7?
yeah. So if I can just grab it from the inside. So if I use 7, update,
Yeah.
and then when I change it to 6, it goes back.
That's cool.
So that's why localization, like April tag localization, is really important, because without it, we always have to rely on our odometer, our real odometry, which can slip if we accelerate really fast, then it's not good. So yeah, that's kind of all the stuff you need to know for this. And then this is how we're doing our auto line right now. So basically, you have 3 PID controllers, one to control X is this way, one to control Y, which is this way, and one to do rotation. So you basically, it's basically, you take the first pose I showed you, which is robot pose in target space, and basically what it does is, this pose, you can see it here, it's about 3 meters away from it, it's about 0.5 meters to the left and right of it, and it's about half a meter up, like floating, but we don't care about that. So basically what it does is, it takes that pose relative to the target, and it
What is it?
the robot.
Oh, okay.
The robot's pose relative to the April tag, and it calculates the velocity it needs to go to. It needs to go sideways, so the X speed, or sorry, X is forward. How fast it needs to go forwards, how fast it needs to go sideways, and how fast it needs to rotate. And then this is the same. This code is the same as whenever we're driving, so it basically uses the drivetrain code.
Okay.
That's it simplified down. These values, you don't need to know what these positions are. Those are just there. Those just tell it. It's kind of complicated. But then, that's basically it. Do you guys have any questions on like the Limelight stuff, the auto line?
Wait, so how do you turn it into based off how you want it to?
If it's like, so same thing how we do PID tuning for the arm or for the elevator.
Okay.
We look if it's like really jittery, then the P value is too high. If it's like really slow, then the P value is too low. For something as complicated as this, you can see we only use KP, we don't use KI or KD, because it's like really complicated to tune those. At least for this use case, you don't need it as well. Because friction provides a lot of the dampening that KD would do.
But y'all didn't tune it here?
No, we did. So, in our constants, you can see we have all of the auto line constants. So, using these, we can tune it. And then, that's about it. Any other questions? That was a good question. How to tune it. Nothing.
Wait, look, you still don't get it.
Don't get one.
Wait, in the code, can you show the part where in the code that it actually like executes what you want it to do?
Yeah. So I'll explain this in more detail. Then, I guess. Basically, you set the set point. So our limelight is actually a little bit to the off center, right? So we set, or not here. We set the offsets left or right here. X is always going to be the same, right? Like if you're left branch or right branch, it's still going to be the same distance away from the April tide. So that's always the same. And then this angle, so the bot angle relative to the reef always wants to be as close to zero as possible, right? So we don't need to change that. And then whenever we're executing, so this is run like on a loop. We first check to see if the limelight, the April, we see if the robot can see the tag. TV is the value to see if there is a tag present, and then if there is, then get the robot pose in target space, which is what we saw over here with this, and then after that, then we calculate the PID for, this is our X position, this is our Y position, this is our yaw, so our rotation. And then you take those, you take the error, so you take the difference between our X position and what we want our X position to be, and you multiply it by KP, and then you do the same thing for these two. And then once you calculate everything, then you tell the robot to run at those velocities. So you go forward at, for example, 1 meter per second, go sideways 2 meters per second, and rotate, I don't know, 30 degrees per second.
And this is saying
There's everything. This is just telling it if anything's not at its set point, then reset the timer that says to stop. Because after a certain amount of time, it just starts kind of jiggling about. So we don't want that. So we have a stop timer so that whenever everything's in place for like a certain amount of time, then we just stop the command.
I'm the director of modeling. Like that's the director.
Oh, you're the race director.
Yeah.
Anything else?
Like he told the channel because like we were.
I'll get to that. Does that make more sense?
yeah.
Hopefully it works.
You're in English.
It works. It works.
Okay.